Welcome to another edition of 18 Minutes With, co-sponsored by the Kavli Prize. I'm Steve Mirsky with co-sponsor Scientific American Custom Media. For today's chat, we welcome John Pendry. He's a physicist at Imperial College London and was a co-recipient of the 2014 Kavli Prize in Nanoscience. And there he is. Hello, Professor Pendry. Nice to see you there.
Hi,
We'll talk about
Steve.
your work. And on screen, you in the audience can see how you can ask any questions you might have that you think can add to this discussion. Dr. Pendry, we're going to get to your research into the invisibility cloak. We have to do that because we have many Harry Potter and Star Trek fans out there who will
That's
be
okay.
upset if we don't talk about that. But first, let's talk about you were awarded the 2014 Kavli Prize in Nanoscience for, quote, contributions in optics that broke long-held beliefs about the limitations of the resolution limits of optical microscopy and imaging. That might sound a little dry, but it's not. It's really quite fascinating. What did you do, and why is that important?
Well, it solved the problem. And the problem was posed many years ago when people started to make really perfect or very high quality optical equipment. And the laws, it's not really a law, but the rule states that you can only see things with an ordinary lens that are the same size as the wavelength, roughly, a little bit less than the wavelength, maybe. And that length is about half a micron. Today's world involves nano objects. Um, Primarily, you might think in electronics and so on, where the dimensions in your computer chip are of the order of 10 nanometers. So that's a hundredth of a micron. But also in biology, when biologists want to see inside the cell, and the cell starts to reveal its interest at about the tens of nanometers level. And that you can't do with a conventional lens. So the focus of our research is nano optics and learning to control light on the nanoscale so that we can use it in the context of modern science.
The, None of these things that you're looking at can be seen with the naked eye. Is that correct?
That's correct, yes. You have to, if you wanted to see them, you'd have to use something like an electron microscope. But the problem with the electron microscope is that it uses high energy electrons and they're highly destructive. So you kill the thing that you love, as it were, if you look at it with an electron microscope. That's a little bit bad mouthing the electron microscope, but it's why the electron microscope hasn't gone further than it has.
And what was the practical upshot of this kind of improvement in the ability to see these ultra small objects?
Well, it's let me first come to there are many applications, only one of which is seeing things. All right. So I said controlling light. So you might, primary use of light on the nanoscale is to convey a signal and communicate between parts of a chip and so on. But of course, imaging is one of the important aspects to it. And it opened the gate to the possibility that we could actually see things with light on the nanoscale. Now, how do we do that? And I should explain that a microscope has two sides to it, both of which have lenses. So the side which everybody will be familiar with, which is peering down the microscope and looking at some bright object on the specimen stage. The other side of the microscope is how you gather light to illuminate the specimen. And usually in an ordinary microscope, that's just a simple condenser that uniformly illuminates things. But there's a more subtle way you can put light onto a specimen, and that's to structure the light. So you might just have a single photo detector looking at what's bounced off the specimen. But if the specimen's illuminated in a very special way, which you can change with time, the simplest example would be scanning a spot of light across it, but there are more complex patterns you could illuminate. And that is the way that we are using uh, nanolight to see very tiny things. There's a grant which University of California, Berkeley has from the Moore Foundation, which is to use structured light to illuminate biological samples so that it can be resolved on a length scale without damaging them, as some other forms of microscopy would do.
And that would probably be very useful for biomedical applications. But the ability to control the light itself is a fascinating thing. And you've been credited with uh, developing what's called a perfect lens, which was thought to be impossible. What is a perfect lens, and why is that an important thing to have come up with?
I explained that with an ordinary lens, you can only resolve so much of an object on a certain length scale. And it's not because light doesn't reach all the parts of an object. So if you have some molecule emitting light in some biological sample, a dye molecule perhaps, and you were able to go in really close to that molecule, you would see all the details down to the nanoscale and beyond. So light near the object is highly structured. The issue is that only part of that light escapes, um, and some of it remains near the object. That's called a near field because it stays near to the object. And the trick which this lens performs is it is able to grab hold of that near field and persuade it to leave the object so that you can then get it into the lens, process it, and turn it into an image. Um, Now, the technology for doing that was available in a sense that you could, if you knew your equations really well, anybody in the last 150 years could have shown how to do it. But for some reason they didn't, and it was me who stumbled across it, almost by luck.
So there didn't have to be any new physics developed during the whole of the 20th century to take this on, but you
No,
saw
it's
a way
all
to
old
do it.
stuff. In fact, my third year undergraduate students could have done it had they not been down the pub having a beer.
It's well, you never know. The beer can be an inspiration as well. Um,
Certainly can.
what's going on in optical microscopy and imaging since you were awarded the Kavli Prize, and what kind of applications might we see related to those developments?
Well, although I'm a theorist, and my prescription for the perfect lens is a theoretical one. It's a correct theory. There's been a lot of argument about it, but it's generally agreed now that it's a correct theory. But that's only one step towards making things a reality. Uh, to make a perfect lens, you have to have perfect materials. And since the ordinary glass lenses have been around for thousands of years, people have had a lot of practice in making them really good. The perfect lens has only been in evidence for a couple of decades. And so people are struggling to get the right materials to make it work. It turns out that, strangely enough, metals, which you'd think of being opaque things, are strangely transparent to this near field that I mentioned, which is the missing component of the image. So people are working with metals such as silver to uh, to gather the near field and structure it to make it into an image. More progress is being made in using lenses not to make an image, but to focus radiation. So, for example, one application of this technology is to uh, deliver cancer drugs. So if you take a silver nanosphere, it will perform this trick of concentrating light on the nanoscale. That actually was known before the perfect lens, but that's one application of nano light. So silver or actually gold, because it's less reactive to drugs and so on, you decorate a gold nanoparticle with some drug, which is in a deactivated state. You then inject the gold nanoparticles into the patient, and it circulates in the body. And it turns out that cancer cells have very large vesicles, and they can emit the gold particle very easily. And once it's into the cancer, you illuminate it with laser light, and the laser light is concentrated in the gold nanoparticles. So if there's no gold nanoparticle there, the light's not strong enough to hit the drug. If it hits the gold particle, it concentrates it down to the nanoscale, very intense, activates the drug, and then the drug goes for the cancer. So that's one application that there's
Mhm.
been. Other applications are it's difficult to make light talk to light. So electrons are used for computing and so on, uh, partly because of their electrical charge. So one electron knows very well if there's another electron close by it, and so you can switch electrons, electronic circuits very easily. That's more difficult with light. Photons pass by one another without even saying hello. So to make light talk to light is very difficult, but the trick is nano focusing again. So if you can focus light down to the nanoscale, it will, first of all, it will interact with the electrons in the particle that's focusing it, and then these electrons will respond and they will enable it to talk to other light. So there's a meeting place for photons if you can focus them very strongly. And so controlling light with light is a neat trick which you can do using these nano focusing techniques.
Well, I think we should get to the invisibility cloak so that everybody can be satisfied. You developed this idea at the microwave wavelength, and you presented it at a conference. Uh, in your words, you thought it was kind of a joke. You wanted to just show an extreme example of what you could do with controlling light, and you expected the audience to laugh, and they did not laugh. They were taking it very seriously.
They offer me money.
So where are we with invisibility? And obviously, we're not unless Harry Potter was maybe a centimeter tall. He probably couldn't get away with an invisibility cloak, but even then, he'd have to stand very still. So
Yeah.
what's the theory behind invisibility, and what's the reality?
Well, the theory is what you have to do to make something invisible has been evident for a very, very long time. I like to put it in terms not of Harry Potter, but Peter Pan. If you recall a story of Peter Pan, he was the little boy who lost his shadow. And you can paint something black, which is conventional stealth, and you won't see it, of course, in the sense that it doesn't reflect any light, but you know it's there because it casts a shadow. So if you play squash, for example, you play squash with a black ball, and it's highly visible because you play it in a court, which is very brightly lit. So the real challenge is to make something lose its shadow, and that's been known for a long time. It's fairly obvious. But how do you do that? How do you make light pass around an object so that even though it avoids the object, it's undisturbed? And that was a first-rate challenge in theoretical physics. How do you make light do exactly what you want? And the technology we're developing was actually separate from the perfect lens thing, though they can be related. It's a way of controlling light, which is called transformation optics. And this was a showcase for transformation optics that you could, at a stroke, design a cloak that, again, was in principle perfect. Um, that did all these things that people have been wanting to do for a long time. And I should mention at this point that my co-conspirator in this is David Smith, based now at Duke University, and it was his team who took a theorist's dream and made it a reality with a cloak for radio frequency materials, and later came the optical cloak.
And we're not going to see any flexible cape that we can throw around ourselves and become invisible anytime soon or ever.
No, it's the cloak is something of a misnomer, because in order to do its job, it has to have a finite thickness. I always say it's more a case of Harry Potter's shed than Harry Potter's cloak.
Right. And entire interstellar spacecraft being they're more likely to go at faster than light speeds than to get cloaked, probably.
Yeah, they are. But that's, I mean, the concepts that arose for the cloak were actually developed during a consultancy I have with the Marconi company on stealth. We were specifically looking at the stealth. And even though you're not going to see a perfect optical cloak that can flap around, the technology can also do other clever things, such as there's a technical term called spoofing, which means that you make something appear to be something that it isn't. And using these techniques, you don't need to cloak something. You can make something which is quite a fearsome vehicle, like a submarine or an aircraft, appear as something very, very innocent.
Mm-hmm.
You can also spoof the speed at which it's moving. You can make it appear to move at quite a different speed from what it is, and that would throw off a lot of attacks. More innocent application. Sorry, go ahead.
We have an audience question. Is this cloaking related to stealth technology in the military? And stealth technology is basically just making something as dark as possible. Is that right?
It has been so in the past, but that's not really enough, because today, if you flew a cruise missile over New York, you could just call up the mobile phone companies and say, "Hey, I think there's a missile under there. Can you tell us where it is?" Because it would cast a shadow in the mobile phone signals, and they know quite well where the where the object was. So the military is going to have to be much more clever about how it hides things, because conventional pot of black paint is not enough in the future.
I had this thought. I'm sure it wasn't original at all, but about 15 years ago, it suddenly hit me that for a photon that was created during the Big Bang event, no time has passed at all. If that photon has been streaking across the universe for the last 14 billion years, for that photon, it's still the moment of the Big Bang. Is there anything useful about that idea?
Wow, that's a big challenge. I'm sure there's something useful. Whether I'm the man to tell what it is, I'm not sure.
Is the notion itself correct? It's the same instant for that photon, which has been traveling.
Yes, time is compressed for a photon. It's
Yeah.
that is true. Yes.
Figured I'd throw in one of my own um, amateur questions. We're almost out of time. Nominations for the next Kavli Prize close today. What has the prize meant for you, and why would you encourage others to nominate people in the years to come?
Well, I'm very, very happy to be a prize winner. I think there are two facets to the Kavli Prize. One centers on the prize winner, And for the prize winner, it's very nice. They make a lot of fuss of you. There's a ceremony. You meet a lot of interesting people, and you get some money, which is also nice. But there's another, perhaps more important aspect, and that is these grand prizes, if you like, the Kavli, primarily the Nobel, of course. They attract a lot of publicity to science, and they're one of the few incidents in scientific life that attract the media. And the media, through the media, you can make presentations of what's important in science, who the people uh, driving things forward are, and so on. So that public relations side is something which Kavli do very well indeed. And a third aspect, you might say, is one's own career. That if you receive one of these prizes, then through the publicity, you get a lot of recognition in your own institution, which might not have come your way in such a massive style before. And also, you get a lot of young people writing to you saying, please, can we come and work with you? Which is a nice thing to happen.
Yeah.
Of course, we all have collaborators and students. So
Well,
yes, very positive about it, obviously.
that's great. It's been a real pleasure to speak with you today for a little bit. Just want to say the Kavli Prize recognizes scientists for pioneering advances in the fields of astrophysics, nanoscience, and neuroscience. The Kavli Prize is a partnership among the Norwegian Academy of Science and Letters, the Norwegian Ministry of Education and Research, and the US-based Kavli Foundation. Kavli Prize winner John Pendry, thank you so much for joining us today.
Thank you. Thank you.